my subject for today's discussion with you is a very brief review of signals and systems, because I believe there are some of you who might have slightly lost touch with the subject because there is a gap of about a semester or a year for them, right? So I just want everybody to be on equal terms here, and this is important for all of you, that you have a very good solid background in signals and systems, as I mentioned earlier also in the discussions. Now before I do that, let me complete the discussion we were having last time about communication channels. If you remember, I discussed a variety of communication channels with you, particularly channels which are relevant to us, namely electrical communication channels. By practically every one of these channels is some kind of an electromagnetic wave channel. It could be a free space propagation channel like we have in the atmosphere or in free space, or it could be a guided electromagnetic wave channel, right? The examples of guided electromagnetic wave channels are the pair of wires through which you can communicate, let's say as you do from your home to a telephone exchange, or a cable, coaxial cable, which can carry much larger number of signals than a pair of wires can because of the larger bandwidth it can support, or it could be an optical fiber, right, which can support an even larger bandwidth. And here there is a small comment I would like to make and ask all of you to think about it. Typically, as you go up in the carrier frequency or center frequency of operation in a communication channel, if you are able to do so, it increases your ability to take up larger bandwidth. It supports a larger bandwidth, right? Why is it so? Think about it and we'll discuss it sometime. Alright? For example, why do we use optical communications? Why do we use fiber optic communications? Because it has the capacity to offer you much larger bandwidth than, let's say, microwave communications can do, or even larger than a coaxial cable can support, and so on and so forth. So it's an issue which I'd like you to think about before I respond to this. Now let's come back to our subject of interest today, which is a very brief overview of signals and systems. Now to start with, let me start at the very beginning. And if you remember, you must have dealt with a representation of signals in terms of first starting with the most basic signals. Well, to start with, if you remember, we can classify signals into two kinds, namely deterministic and random signals. So we are talking about signals right now, and in communications we deal with both kinds of signals, because deterministic signals are useful to us as, for example, as carriers, right? We use a sine wave as a carrier of a certain frequency, right? And deterministic signals are also useful in generating synthetic signals of various kinds. But random signals are absolutely characteristic of communications. Why? Because most of the time the information that is of interest to you is typically unpredictable in its form, right? And therefore it is random. Even the speech waveform that is coming out of a person's speech, voice, is an unpredictable waveform to a large extent, right? To some extent it is predictable, but to a large extent it is quite unpredictable, and therefore it is quite random. Similarly, the noise that you encounter in a communication system can only be modeled as a random signal. Now, right now I will not review the random signals part. I will only look at the deterministic signals. The most basic kind of deterministic signals which you come across are complex exponentials and sinusoidal signals, real sinusoidal signals, right? So if you take a real sinusoid, like a very simple signal like this, right? We know some of its features, but as you must have already learnt that you can express a real sinusoid or cosinusoid in terms of complex exponentials, and it's much easier to work with complex exponentials in many instances than with the corresponding trigonometric function. Right? So in fact the complex exponential you can think of as a rotating phasor, and the cosine signal can be thought of as a resultant of two rotating phasors which are moving in opposite directions, one in clockwise direction and the other in anti-clockwise direction. So you can think of this as real part of, let's say, this complex exponential. Now this is very basic stuff, but it is useful to review this because sometimes people forget the basic stuff and they have difficulties later. So this is the, let's say, the phasor which is rotating in the clockwise direction. If it is in the clockwise, then this is the sum of these two phasors. The other one rotating in the anti-clockwise direction, as indicated by this negative sign in the exponent. Similarly, if you have let's say a signal like this, this is just an example. Right? You can express it if you were to carry out some simple trigonometric manipulations as e to the power j 10 pi t minus 2 pi by 3 plus e to the power minus j 10 pi t minus 2 pi by 3. So whether you are working with a cosine wave or a sine wave, you can think of it as sum of phasors, and phasor is a complex exponential rotating either clockwise or anti-clockwise. Right? And this term in the phasor indicates the phase, initial phase of the phasor. Do you have any questions? Have I made any mistake? This should be minus, yes, correct. That's right. So 1 upon j. So 1 by j. Good. This is 2 by 3. I think this is okay. Actually, I'm sorry. This is correct. There is a mistake. You please check it out. Please check it out. What I written is absolutely correct. Yes, you have confused me. Right? You have, because you have to first, the way I have gone over it is first express sine in terms of cosine and then written it in those terms. Right? Please check it out. This is just an example. I do make mistakes at times, and I like you to correct me when I do make mistakes. But if I don't make mistakes, don't make me make mistakes. Okay? It's all right. Now, as I said, the sinusoids are some of the most basic kinds of signals in terms of which you work. Why we consider them as basic? First, because they are very easy to generate. Right? For example, a typical oscillator that you might have used in your lab or you might have learnt about in your analog electronic circuits are likely to learn soon, naturally generates a sine wave. Right? Oscillations are in the form of sinusoidal oscillations. That's one reason. The other reason is many other deterministic signals can be represented in terms of sine waves. For example, that's what Fourier series is all about, which I'll review in a few minutes. Right? Now, just like sine waves, there is another set of basic signals which are quite different in nature. Sine waves are infinite duration signals extending from minus infinity to plus infinity. They are periodic signals. Right? As against this, you can have a very different variety of basic signals which are very useful in the concepts and signals in some communications, signals and systems. And one of those basic kind of signals is the impulse function. I'm sure all of you know very well about it, and let's quickly review what is the definition. There are two ways of defining the impulse function. Well, several ways, not just two ways, there are several ways. Because since this is a review, I will not go into a very detailed description of all those various methods. All we will say is that an impulse located at t equal to 0 is denoted by delta t and is defined to be a function which encloses a unit area under it, and it is 0 everywhere other than t equal to 0. So this is a definition of an impulse function, right? This is one definition of a number of possible definitions of an impulse function, right? So some people sometimes write by mistake delta of t equal to 1 at t equal to 0. Now that is wrong, right? Delta of t at t equal to 0 is undefined, is actually infinity, right? But the area under it is well defined, and to indicate that fact, the usual notation for an impulse function is something like this. This is the time axis. Suppose the impulse is located at t naught, then we will write this as, so this is your time origin, this will be the impulse located at t minus, and this arrow here indicates that the amplitude of the impulse is infinity or undefined, right? And but the area under it is 1. If it is k times delta t minus t naught, everything remains the same except that we say that the area of the impulses, area under the impulse is now k, or the strength of the impulse is k, right? That's the usual language that is used. Now some of the very important properties of an impulse function are, if you have a time function, so here I will just quickly review the basic concepts and discuss the basic properties. I will not discuss any proofs here because the idea is to make you recollect these things more than anything else, right? Well, if you don't understand something of this, I would suggest that that's what you should look for when you are reviewing your signals and systems. Let us quickly go through the proofs and things like that. So if you look at this integral of xt multiplied with delta t minus t naught minus infinity to infinity dt, what is the value? Xt naught, right? Very important property, also called the shifting property of an impulse function. Alright? Now sometimes this is also taken as a definition of the impulse function, right? So it's a matter of starting from here and proving this or the other way around. Some of the other properties are, if you scale the time axis by a, then delta of at would be 1 by mod a of delta t, and so on and so forth. The last property that I would like to discuss is, suppose I consider this, just the product of xt into delta t minus t naught. We can also write this as x t naught into delta t minus t naught. Alright? Now another basic signal which is very closely related to the impulse function signal is the unit step function. Pictorially, the unit step function is a function like this. Its value is 1 for t greater than 0, so that is the definition. And 0 for t less than 0. Or it can also be defined in terms of an integral with respect to the impulse function. Integration will be from minus infinity to t, right? As you can see, this would be equal to this, right? So that's as far as basic signals go. One set of basic signals are your complex exponentials, trigonometric sinusoids of various frequencies. Then we have the impulse function and the unit step function, and there are several functions which one can derive from these basic functions. We quickly now look at Fourier series, because I am trying to collect practically all the important concepts of interest to us in this course into this lecture, right? So we will quickly review all of these things. Okay. Before we talk about Fourier series, you remember that Fourier series are defined for periodic signals. So we have to talk about periodic signals. We say that a signal is periodic with period t naught if x of t plus t naught is equal to x of t for all values of t and for all values of t and for a given t naught. Right? Now, if it is periodic, then we can represent the signal x of t in terms of exponentials of period 2 pi by omega naught and its its multiples. Actually, frequency is omega naught and its multiples, right? So we can represent it in terms of some coefficients x of n e to the power j 2 pi omega 0 t, where omega 0 is 2 pi by, is there a mistake here? It should be 2 pi n omega 0 t, right? N going from? I'm sorry, it should be either f 2 pi f naught t or n omega naught t, right? So let me change that to 2 pi n f naught t, where f naught is 1 by 2 pi of omega naught. And this representation is valid over a period, or so if you take any period between t0 to t0 plus capital T sub 0, t sub 0 to t sub 0 to plus capital T sub 0, this representation is valid. It's valid for any period of the function x of t. The coefficients xn in this Fourier series are given by integral of xt e to the power minus jn omega naught t. This is what you wanted to tell me to write, right? So this should be let's say t0 to t0 plus t, capital T0, right? And these coefficients we call the Fourier coefficients of the signal x of t, right? So here we have a representation of the periodic signal x of t in terms of a set of an infinite set of coefficients, and going from minus infinity to plus infinity. This is a so-called complex form of the Fourier series. You also have real forms which use trigonometric functions cosine n omega naught t and sine n omega, right? So these Fourier coefficients represent the signal in what we call the frequency domain, right? You can say x of n is a coefficient which has an amplitude which you can call mod of x of n, and which has some phase which you can call as the angle of x of n, or call it theta n if you like, right? This amplitude and this phase information represents the amplitude and phase of the nth component in the Fourier series. The nth component being e to the power j n omega naught t, right? Now, and therefore we call this as the amplitude spectrum of the signal. When we plot x of n against n is an integer here, going from minus infinity to plus infinity. So if I plot x of n against n, right, it will be a discrete plot. The plot will be in the form of lines. It will be a line spectrum in this case, right? So if I plot mod of x of n against n, that gives me the amplitude spectrum of the signal. If I plot theta of n against n, that gives me the phase spectrum of the signal. Now for real signal x of t, so I am looking at some properties of the Fourier series now. For real xt, what can you say about x of n? In particular, if I ask you the relationship between x of n mod and x of minus n of mod, what will be the relationship? They are equal, right? Similarly, if you look at the angle of x of n and the angle of x of minus n, what is the relationship? They are negative of each other, right? We say that the amplitude spectrum is an even symmetric function and the phase spectrum is a not symmetric function, not for all kinds of signals but only for real signals, real valued signals, right? This can be neatly summarized in the form of a single equation saying that x of n conjugate is equal to x of minus n for real signals. The second most, there are many properties of Fourier series, but since they are very similar to the properties of the Fourier transform, which I am coming to shortly, I will not discuss all of them. They are parallel to each other, right? So if you know some of the properties of the Fourier transform, you also know the corresponding properties of the Fourier series, right? But one property which I like to discuss here very briefly is the Parseval's theorem. Do you remember that? It's a very important result because it relates the energy calculation of the signal in the time domain, energy or power. In this case, should we talk about power or energy? It will depend on what kind of signal we are dealing with, power signal or energy signal. A power signal is one in which it makes more sense to calculate power because it has a finite power, right? For example, a sinusoid has infinite duration. What's its energy? Infinity, right? So it doesn't have a finite power. It doesn't make sense to, it doesn't have finite energy. So we don't call it an energy signal. We call it a power signal. So on the other hand, a signal which has a finite energy typically will have zero power, right? Because power is defined in terms of energy divided by time as time tends to infinity, time interval tends to infinity. So if the energy is finite and time interval tends to infinity, the average power would be 0. So it makes more sense there to talk about energy rather than power, right? So for sinusoids, for periodic signals in general, they have to be necessarily of infinite duration. A strictly periodic signal has to be of infinite duration, and therefore it is better described in terms of power than in terms of energy. So here we talk about power, therefore, which is the power calculation here would be, you look at the integral of xt mod square dt over any period t0, right? That's the average power and divided by t0. This, by Parseval's theorem, can be obtained by simply summing the magnitude squares of all the Fourier coefficients. Very interesting result, right? You sum the magnitude square of all the Fourier coefficients, that gives you the average power of the signal. So now we quickly come to Fourier transforms. Now, unlike the Fourier series, which is defined only for periodic signals, Fourier transforms are defined for any signal. Strictly speaking, the periodic signals, but through some clever mechanism, it can also be made to represent periodic signals, right? Very clearly by the use of impulse functions in the frequency domain. You will be remembering that. So if you have a signal x of t which is no longer necessarily periodic, then I can define its Fourier transform x of f as integral of xt e to the power minus j 2 pi ft dt. Right? If you look at this, this integral is very closely related to the expression we have for x of n. Right? In fact, you can derive this expression through a limiting procedure on the Fourier coefficients. Right? Where, what is a limiting procedure like? Do you remember? You make the period, first start with a finite period with a periodic signal, and then you make the period infinity, right? And you get to the Fourier transform. And the important thing is the line spectrum of the original periodic signal now becomes a continuous spectrum, right? Continuous in the frequency domain. So x of f is a frequency domain description of x of t, and one can reconstruct x of t from x of f by taking what is called the inverse Fourier transform, which will be x of f e to the power plus j 2 pi ft df. Right? If you write it in terms of omega and d omega, then we have to put a 1 by 2 pi, not otherwise. Right? So once again, x of f is called the amplitude spectrum, and the angle of x of f as a function of frequency is the phase spectrum of the signal. Right? So you could write x of f, let's, if I call this theta of f, then x of f can be thought of as mod of x of f e to the power j theta f. Right? Now there are certain conditions which the signal x of t must satisfy in order that the Fourier transform exists. Right? I will simply name the conditions. These are called the Dirichlet conditions. There are 3 of them in number. The most important of these 3 conditions is the requirement that the signal be of finite energy. Right? That is, it is square integrable. There should be a magnitude square integrable function of time. Right? So please review these conditions yourself. Now a quick review of the properties, the most important properties of the Fourier transform. Some of the properties are the same that we already discussed in the context of Fourier series. So for a real signal x of t, x conjugate f would be equal to x of minus f, which is again equivalent to saying that the magnitude spectrum is even symmetric and the phase spectrum is an odd symmetric function of the frequency for real valued signals x of t. Right? So need not spend too much more time on that. Similarly, the so-called Parseval's theorem, which incidentally is sometimes also called the Rayleigh's energy theorem, is also valid here. So the equivalent of the Parseval's theorem here would be that if you look at, now it makes more sense to talk about energy here, because in fact the Fourier transform, the existence of the Fourier transform is only for finite energy signals, although we can extend this definition to periodic signals as a special case, but generally Fourier transforms are defined only for energy signals, because that's a condition we discussed. Right? They should be square integrable. Right? So it makes more sense to talk about energy here. So energy means I will simply integrate mod xt square between minus infinity plus infinity. This is the same as integral of, if you look at the frequency function, that is the spectrum, sometimes x of f is simply called the spectrum of the signal, and spectrum has an amplitude part and a phase part, right? So if you take the amplitude part of that and square that, integrate that over the entire frequency range, these two integrals are same. That is, you can calculate the energy either by a time domain operation like this or by a frequency domain operation like this, whichever is convenient. Right? Now let's look at a few other important results of Fourier series. These are the same Fourier transforms. These are the same as we discussed for the Fourier series. Please stop me, or if you have any questions, please point it out, or if you find there is a mistake. The next important result that I would like to mention without proof, like all other results, is the so-called convolution theorem. Now I have not yet discussed the concept of convolution, which I will discuss separately when I discuss linear time invariant systems shortly. But basically, assuming that all of you know what is convolution, then the result is like this. If you have, okay, let me briefly review what is convolution. If you have two signals x1t and x2t, then I say that x1t star x2t is a convolution of xt, where this operation is defined in terms of this integral. Right? This integral represents the convolution operation. And then convolution theorem says that the convolution of x1t and x2t, if x1t has a Fourier transform of x1f, x2t has a Fourier transform of x2f, then x1t convolved with x2t have a Fourier transform which is the product of these two corresponding Fourier transforms. Right? This notation will be used to indicate that these quantities on the left hand side and the right hand side are Fourier transform pairs. Right? This is a very, very important result, as we will discuss shortly in the context of linear time invariant systems. Then there are the standard linearity properties and the time delay properties, which are skipped. Linearity means the Fourier transform is a linear operation, right? That means if I take a linear combination of two signals, the Fourier transform would be a linear combination of the corresponding Fourier transforms of the two signals. And the time delay property, of course, let me just briefly mention that. If x of t and x of f are Fourier transforms, then x of t minus t naught will have a Fourier transform which is x of f e to the power minus j2 pi f t naught. Right? That's the time delay property. Scale change is another important property, which says that if I modify the time axis by a scaling factor of a, it will modify the frequency axis in the opposite direction. For example, if a is greater than 1, then the frequency axis will be scaled by 1 by a, which will be less than 1, and so on and so forth. So more precisely, the result is, this is a intuitively very interesting result. Basically what it says is that if you have, essentially it implies that if you have a signal which is of small duration in the time domain, it will have a large span in the frequency domain. Right? If you compress this time axis, it expands the frequency axis, right? And vice versa. Right? So it has it's a very interesting result, and also leads to a very interesting concept, which I, if time permits, discuss later, and that is the so-called uncertainty relation in communication theory. Have you heard of that? Like you haven't, I'm sure you heard of the uncertainty relation in quantum mechanics. There is a corresponding uncertainty relation of communication theory, which says that you cannot locate a signal precisely in time as well as in frequency together, right? Arbitrarily. There is a limit to, either you can locate it very accurately in time or very accurately in frequency, but not both. Right? Think about it, and we'll discuss it sometime. and this is a consequence of this property of the Fourier transform pairs. Another interesting property is that of duality. I'm doing a very quick review because we have gone through a course in signals and systems, and this is just meant to brush you up on this matter. So duality is interesting. If you construct a time signal which has a shape of the Fourier transform of the signal, right? Of course, this will imply that x here is maybe a complex valued signal, right? If you consider a time signal which has a shape of the Fourier transform of small x of t, then the Fourier transform of this would be small x, the original time domain signal, with f replaced with t replaced with minus f, right? So this is the duality result. The next we come to a very important result, a property of the Fourier transforms called the frequency translation theorem, and this theorem is particularly useful in our course, particularly when we discuss the modulation techniques. This theorem states that if I multiply a time domain signal x of t with a complex exponential e to the power j2 pi f naught t, then its Fourier transform gets translated to the frequency f naught. That means multiplication of x of t with a complex exponential of frequency f naught shifts the spectrum of x of t, or the Fourier transform of x of t, to this center, to f naught as a center frequency. So its centering, suppose the original signal is centered, its spectrum is centered to 0 frequency. After this multiplication, its spectrum gets centered to the frequency f sub 0. This is also similar to what is also called the modulation theorem, in which you multiply x of t with a real cosinusoid like cosine 2 pi f naught t, and now since this is equal to the sum of e to the power j2 pi f naught t and e to the power minus j2 pi f naught t, this gets shifted, the spectrum of f(x) t gets shifted to both f naught as well as to the frequency minus f naught. In other words, pictorially speaking, if this denotes the spectrum of xt which is centered at 0, multiplication of x of t with this leads to a spectrum like this. Whereas multiplication of x of t with sine wave or cosine wave leads to a spectrum like this. That is, this gets shifted to both f naught as well as to minus f naught. Now these theorems play a very crucial role in modulation techniques that we are going to discuss in this course. In fact, it forms a basis of one of the most important functions of the transmitter, namely to modify the center frequency of a signal. This is also very useful in receivers when we want to bring a signal from an RF frequency down to a baseband frequency. The next result, which is important to some extent, is the differentiation theorem and correspondingly the integration theorem. I will just state the result without proofs. If you take the nth derivative of the signal x of t with respect to time, and the corresponding Fourier transform is a product of the Fourier transform of x of t with a factor which is equal to j 2 pi f to the power n. Similarly, the reverse result holds when you integrate a signal x of t from minus infinity to t. The Fourier transform now is given by this, plus there is a component which is proportional to the DC value of the signal. There is a scaling factor here which you may check out from the book. This in a nutshell is the Fourier transform. We have looked at some of the most important properties of the Fourier transform. This treatment is not exhaustive, and it will be very much appreciated if you were to review the entire set of properties of the Fourier transform on your own. I next move on to systems. A system is a model for some physical system or some process. So when we do system modeling, a system, for example, could be a circuit, could be an electrical circuit, it could be a mechanical device. It could be a weather system, it could be anything. The way we will look at a system in this treatment is that it has an input and it has an output. And when we talk about system modeling, primarily we are looking at trying to understand the relationship between the output and the input of a system. So when we study the input-output relationship of a system, we call this system modeling. From the system modeling point of view, it is this relationship which is important more than anything else. We look at the system, in fact, as a black box. It doesn't matter what it is internally comprised of. It will be comprised of electrical devices, electrical components like resistors, inductors and capacitors. It could be mechanical components like springs and dampeners and whatever things you may have in a mechanical system, etc. What we like to understand is how we understand the response of a system in relation to some excitations that may be given to it. Now, from this point of view, it is convenient to think of the system as an operator. The operator H here operates on x of t, the input signal x of t, to produce an output y of t. Under certain conditions, the operator H is said to correspond to a linear time invariant system, and these are the kind of systems which will be of greatest interest to us. It does not imply, of course, that communication engineers do not deal with systems which are not linear or which are not time invariant. However, a large part of our treatment will be devoted to handling systems which are LTI systems, so to say, and therefore it is useful to review what LTI systems are all about. We say that the system is linear if the superposition principle holds. In other words, so linearity implies that if the system responds to a signal x1t to produce an output y1t, responds to the signal x2t to produce an output y2t, then if I excite the system with a linear combination of these two inputs, namely alpha 1 x1t plus alpha 2 x2t, then the system will respond by producing an output which is a corresponding linear combination of y1 and y2. and by time invariance, in addition, the system should satisfy the homogeneity property. That means if I give a 0 input to the system, the output is 0. And by time invariance, we mean that the system response is independent of the time of excitation of the input signal. So if the xt produces an output from the system which is y of t, and if I delay the input by t naught seconds, the response does not change in nature. All that happens is that the response is correspondingly delayed. In other words, until the input comes, the system does not respond, or the system responds only by corresponding delay in the input or in the output. Now, from the point of view of describing input-output relationships, it is important to understand or important to develop some kind of a characterization of the LTI system. It so happens, it's very easy to check out that for an LTI system, this characterization is very easy and can be done by the response of the system to an impulse. This response, usually denoted by h of t, is called the impulse response of the system. The significance of the impulse response of the system is that in view of the linearity of the LTI system, and in view of the fact that any signal x of t can be expressed as a superimposition of suitably scaled and suitably time displaced impulse functions, it is possible to express the output yt of the signal in terms of a linear combination of the response to these impulses, and this is best expressed in terms of the convolution relation that exists between the input and the output, which is given by this. That is, given the input x of t and the impulse response ht of the system, the output can be expressed through this superposition formula, which is also called the convolution integral, which is a manifestation of the superposition property arising from the linearity of the system, and usually expressed in terms of shorter notation like xt convolved with ht. So this is a notation for convolution, or it's the convolution operator. Finally, we just note two other important attributes of an LTI system. One relates to causality. We say that a system is causal if this is of course not the definition of causality, but it's a test for causality. If the system impulse response ht is equal to 0 for t less than 0. This is a test for causality. Definition of causality is that the system responds to an input x of t. We can put it like this: until there is an input, there is no output, right? So, since the impulse response corresponds to an impulse occurring at t equal to 0, there can be no output of the system, no non-zero output of the system before time t equals 0, and hence the impulse response has to be 0 for t less than 0. Another attribute of a system which we shall assume throughout our course to be valid for the system that we study is stability, and stability refers to the bounded input bounded output property of the system. That is, if your input xt is always guaranteed to be less than certain finite value, then the output y of t will also be guaranteed to be less than some constant value k, and if this is so, we say the system is, if every such input the output satisfies this property, we say that the system is stable. And the test for stability is that the integral of the modulus of the impulse response should be bounded, should be less than infinity. So I think with this I will finish the review for signals and systems, and next time we will consider a very important new result for you, and namely introduce the concept of the Hilbert transform, which we will find is extremely useful for studying signals of certain types which we encounter in communication engineering. Thank you.